Pickering Governor. A Pickering Governor is mostly used for driving gramophone, right? It's an old musical instrument. It consists of 3 straight leaf springs, right? So we know what a leaf spring is, right? Arranged at equal angular intervals round the spindle, so at usually 120 degrees. Each spring carries a weight at the center, right? Each spring carries a weight at the center, right? So here in this picture only 2 of the leaves are shown because one would be on the back side, right? So it cannot be shown. So each spring carries a weight. So this is a weight at the center. Okay. The weights move outwards and the spring bend as they rotate about the spindle axis with increased speed. So we know when this system moves, right? When this one moves, what will happen? This weight will tend to move outside. This weight will also tend to move outside. So due to that, this will take a kind of bend, right? So this is how the functioning of Pickering Governor. Okay. In this figure, the governor is at rest, right? So here you can see it is at rest. So when it is at rest, it's straight. Okay. But when it starts moving, this will bend based on the centrifugal force of this weight. When the governor rotates, the springs together with the weights are deflected as shown in this figure, right? So it will deflect like this. The upper end of the spring is attached by a screw to hexagonal nut fixed to the governor spindle, right? So this one is attached to a nut. The lower end of the spring is attached to a sleeve which is free to slide on the spindle. So this one is fixed. So this cannot move. Only the bottom part either has to move up or down, right? So this sleeve will move up or down, and here is the stop, right? So this could be the maximum movement it can. The spindle runs in bearings at each end, and it's driven through gearing by the motor, right? So this may move like this or this. The sleeve can rise until it reaches a stop. So here is the stop. So this sleeve can reach until here. It reaches a stop, whose position is adjustable. So this stop position can be adjustable. Right? This stop position can be adjustable. Right? So this is how a Pickering Governor works. Right? Okay, so there are 3 leaves you can see, right? 3 leaves, and each of it has a weight added on it, right? Right, so 3 leaves, and each of it has 3 weights. So when the speed increases, what's happening? This leaf will move up, and this leaf will deflect. Right? This leaf will deflect, and this leaf will move out. And you can see here, this is the stop. Right? So this is so beyond this, the sleeve can't move. Right? So that's the stop. So based on this motion, the sleeve can move only up to this stop. Okay, but here it's fixed, right? Due to this hexagonal nut, it's fixed. So there it can't slide. Only this portion can slide, right? So this is how the Pickering Governor works. Okay. So we'll see how to solve a numerical on Pickering Governor. So this is quite different from all the other types of governor. Okay, because the formula or solution for this one is quite different from the other types. For the other types, what we have done, we have either taken geometrical positions or we take moments, right? But here we are not doing those. We'll see how to do this. Okay. So we'll see the terms first. Let m mass attached at the center of the leaf spring. Right? So this is small m. So mass attached at the center of the leaf spring. So we have 3 leaf spring, mass m. A, distance from the spindle axis to the center of gravity of the mass when the governor is at rest. So when it is at rest, this length is A. Okay. When it is moving, this length is A plus delta. Right. So when this movement is started, it is A plus delta. And omega, angular speed of the governor spindle, right? Omega, angular speed of the governor spindle. Delta, deflection of the center of the leaf spring at angular speed omega. So this delta is the deflection at the center due to angular speed omega. So initially it was A, now it was A plus delta. Okay. Lambda, lift of the sleeve corresponding to the deflection delta. So corresponding to this deflection, there would be some lift, right? So this lift is known as lambda. Okay. Now we see how to solve if any numerical is in this format. We know that the maximum deflection of a leaf spring with both ends fixed and carrying a load W at center is. So we know this formula, right? We know this formula. What's the formula? This is for the leaf spring. We know what the leaf spring is. So while it is at fixed distance and carrying a load, the formula says that delta, right, the deflection delta is equal to W into L cube upon 192 EI, right? Where L is the distance between the fixed ends of the spring, right? So L is the distance between the fixed ends, okay? E is the Young's modulus of the material of the spring, and I, moment of inertia of its cross section about the neutral axis, right? So about this neutral axis, the moment of inertia. So for this type of leaf spring, it is BT cube by 12, right? BT cube by 12, where B is the width and T is the thickness, right? Where B and T are width and thickness respectively. Okay. In case of a Pickering governor, the central load is the centrifugal force, right? So W, right? W equal to FC. Why W is equal to FC? Because centrifugal force is exerted by the central force. Right? So in case of Pickering governor, the central load is the centrifugal force, which is equal to m omega squared into radius. Right? So radius is a plus delta. So while it is rotating, the radius is a plus delta. When it is at initial position without rotation, that is a. Now it is a plus delta. So while calculating centrifugal force, we need to use this R as radius. So m, mass of the ball, R, that is a plus delta, into omega squared, that is the angular velocity while rotating. Okay. Substituting the value W in equation. So we are now going to substitute this W with the rest of the terms. So that is delta into 192 EI upon L cube. Right? So instead of W, right, substituting the value of W in the equation 1, right, in this equation, we will have m omega squared, right? M omega squared into A plus delta, right? Into A plus delta into L cube, right? L cube into 192 EI, right? So 192 EI. What we are doing? We are trying to make delta here as a subject, right? So delta is equal to m omega squared, right? M mass of the ball, omega angular velocity, A plus delta the radius, right? A plus delta the radius into L cube, right? L cube upon 192 EI, right? L cube upon 192 EI. All right. The empirical relation between the lift of the sleeve and the deflection delta is, right? So this is an empirical relationship. So we can use it directly, right? We can use it directly. Lambda is equal to 2.4 delta squared upon L, right? Lambda, that is the lift of the sleeve, right? That is the lift of the sleeve is equal to, right? This lambda is equal to, lift of the lift is equal to 2.4 delta squared upon L, right? 2.4 delta squared, that is the deflection squared upon this total length L, right? So that's an empirical formula which we can use directly. All right. So this is how we, if in case any numerical given on Pickering governor, right? So this is quite different from all the other forms of governors, but quite easy, right? So this formula we know, right? For the leaf spring, the deflection formula we know, right? For the moment of inertia formula we know, right? And also there's an empirical formula given, so we just have to directly apply whichever the given data is.